All right, you guys. Hope you all are having a good day. We are going to be taking a look at the study guide that is posted to Schoology here. Just kind of going through each of the questions, looking at how we would solve each of the problem types and what not. All right, let's just go ahead and get started. So looking at problem 1. We are told that we have a mouse population that is following an exponential model. The population is increasing by about 13% each year. We're given a starting population of 142 mice and trying to, well, ultimately, what we would do with this is use whatever formula we get to figure out what's going on 15 years later. But this problem, rather than kind of tearing away at that whole like 15 years later piece, really just wants us to model what is going on with that population. So when we're thinking about exponential growth, exponential decay, we had 2 different ways that we could set this up. Not really all that different, but 2 kind of basic setups. There was one, which was our f of x equal to a times 1 plus r to the power of x, or there was our kind of continuous growth model, our a naught e to the rt. In this case, we know that our a or our a naught, that's our initial population, that's going to be our 142. And we know that r here, this growth rate, is going to be 0.13. This is our 13%. Note in this case that our R value is positive because we are growing instead of decaying. If we were decaying at 13%, then this would be negative 0.13. And so I would say that the 2 kind of feasible ways that we could set this up would either be to have 142 times 1 plus 0.13 to the x, or, and I guess technically, a little adjustment, this here should be x not t, or that this would be 142 e to the 0.13 times x. Either way here is totally fine. Noting that this one would be if our growth was continuous, and this one if we have like just some lump sum increase all at once. Reality is probably somewhere in between the 2. We would expect population growth to technically be made up of a bunch of discrete events. And so you would not necessarily expect a continuous function, particularly for a population that is as small as the one that we are looking at here. And so reality probably falls somewhere between these 2 functions. But both of these would be perfectly acceptable to use. All right. Number 2 has a very, very similar setup. In this case, we're trying to essentially apply what we see here to kind of what comes next, 2 years later. We are told instead that our R value is equal to negative 0.056. So noticing that that is negative here. This is also important to note. This is in months. Right, so this is like per month here. All right. And we're told that our initial kind of starting amount a sub 0 here, that this is 120 grams. Now, again, you could realistically use either of these models. In the case of radioactive decay, this probably is a lot more going to be modeled continuously. Again, yes, a bunch of discrete events, but in this case, the sheer number of kind of decay events that will happen will be so large that we would expect this to act continuous, but I would accept either model like what we see above. But I'm going to go with the kind of continuous model here. So this is going to be that f of x is equal to our 120 e to the r, negative 0.056 times x, and that f of 2, except it's not f of 2, is it? Because that 0.056 is for months. So how many months are in a year? That's going to be 24 months in a year. This is 120 e to the negative 0.056 times 24, for which I get... This is 120 e to the negative 0.056 times 24. I get about 31.296 grams. Now, this is more than what you would get if you used your a times 1 plus r to the power of x, which is also fine. I believe that amount comes out to being around 30 grams, but either way, perfectly acceptable. All right, let's take a look at number 4. Number 4, how much money will someone make with an account that has a starting value of $10,000? So this is our compounding interest, where A of t is equal to, now it's going to depend whether this is continuous or compounding more finitely. In this case, we are told that we are looking at a continuous compounding. So this is our PERT equation, where our initial amount, that principal, that 10,000, where r here, we are growing, so we would expect positive 0.06, and our t value here is going to be 15. So a of 15 equal to 10,000 e to the 0.06 times 15, for which I get so 10,000 e to the 0.06 times 15. I get that this is 96.03. And you could leave it there. That's probably fine. In this case, with how it's phrased, how much money will someone make from this account? You might want to also deduct that starting value, so subtract 10,000 from it to see the amount of money made, which will be $14,596.03, the excess from what we had with that starting amount. All right. Okay, we're going to take a look at a couple of the problems from 6. Not going to look at every single one, but we'll take a look at a couple. So in this case, we are given 4 to the x equals 9, and we are trying to rewrite this as a logarithm. So we know that if we have b to the y is equal to x, that we can rewrite this as log base b of x equals y. And so for this particular equation, b is equal to 4, our exponent y is equal to x, and then confusingly enough, our x here, our output, is equal to 9. And so we end up with log base 4 of 9 is equal to x. We do the exact same thing for, let's do 9 to the 4th equals x, where again, exact same formula here, not formula, it's just a definition. This is going to be log base 9 of x equals 4. So just using that definition of logarithms, this is something that we should be very, very, very familiar with. I need us to be able to kind of on the dime flip between these two. It will also be helpful for what we do here momentarily when it comes to solving. All right, looking at number 7, again, we'll just do 1 or 2 of these. So we are trying to use the identity property of logarithms in order to solve. Reminder that our identity property is that log base b of b to the power of x is equal to x. What power do I have to raise b to for it to equal b to the power of x? It's, of course, going to be x. So for instance, if I am looking at log base 3 of 1 over 81, notice that I can rewrite this as log base 3 of 81 to the power of -1. And 81 is 9 squared, 9 is 3 squared. So this is going to be log base 3 of 3 to the 4 to the -1. And I combine base to a power, combine these with multiplication. I get log base 3 of 3 to the -4, which is just going to be equal to negative. All right. Likewise, looking at, say, something like log base 2 of 4 cubed, noticing I can rewrite this in base 2. This is log base 2 of 2 squared cubed. Again, multiplying here, I get that this is going to be log base 2 of 2 to the 6th, which is just equal to 6. All right, let's take a look at number 8. So number 8 is asking what's going on with our product rule. How can I properly use my product rule? So product rule tells us that log base b of a product. So when the content of my logarithm is a product, then I can write this as the sum of 2 individual logarithms, log base b of m plus log base b of n. All right, so looking at A here, we have log of 6. How can I reformat this as a product? Well, this is going to be the same as log of 2 times 3, which is the same as log of 2 plus log of 3. And so, yes, this first one would be an accurate way to do it. Now for B, we are given ln of 25 plus 5y, which notably is not written as a product. That doesn't mean that I'm stuck, though. I can, in fact, rewrite this as a product, ln of 5 times 5 plus y. And now I can use my product rule, where this is m and this is n. And so I get that this is the ln of 5 plus the ln of 5 plus y. Am I able to do anything afterwards with this 5 plus y? No. This is completely done. This is as simplified as I would be able to make it. Is that what we see for part B? No, it is in fact not. And so, no, we would not be able to write it in this way. All right, we'll look at one more. This is the ln of 47e. Notice here that product rule can apply, 47 times e. This is going to be the ln of 47 plus the ln of e. ln of e. And ln of e, log base e of e to the 1 is just equal to 1. So this is ln of 47 plus 1. Absolutely correct. All right. Let's take a look here at 9. So we are trying to figure out how to expand ln of x squared times the square root of y over 12yz plus y. The first thing I like to do when we have these really, really complicated kind of insides to our logarithm is let's just start with a fairly simple split. I'm going to start by splitting this as ln of x squared square root of y minus the ln of 12yz plus 1. And then we can deal with each of these smaller logarithms in their own right. Much, much easier to kind of deal with. So looking at my first piece here, this is quotient rule, by the way. If I have ln of m over n, and this is ln of m minus ln of n. So looking at this first one here, this is a product. In particular, this is the ln of x squared plus the ln of the square root of y minus all that same stuff, and using my power rule, dropping down the 2, and then the square root here, thinking that this is to the 1/2, is going to be 2 ln of x plus 1/2 ln of y. Now notice that for our second piece here, it is currently not a product. Can I write it as a product? In fact, yes, I can. This is the same as y times 12z plus 1. And so splitting this apart, I get 2 ln of x plus 1/2 ln of y minus, in parentheses, ln of y plus ln of 12z plus 1. That negative does in fact distribute, and so I get 2 ln of x plus 1/2 ln of y minus the ln of y minus the ln of 12z plus 1. And we could combine some like terms here. So this would be 2 ln of x minus 1/2 ln of y minus ln of 12z plus 1. Just noticing that these two, in fact, can simplify. All right, looking at number 10 here. We are asked to condense 3/2 times ln of 4x minus 2/3. Sorry, 2/3 ln of 3y plus 6 ln of z. Now, honestly, what I would do here, just to make things easy, is probably distribute this 3/2. You could deal with the inside first and then raise everything to the 3/2. That would certainly work. But let's just go ahead. Let's just distribute this 3/2 and see what we get. This is the same as 3/2 ln of 4x minus 3/2 times 2/3 is just going to cancel ln of 3y. That's kind of the nice thing about doing this. And then 6 times 3/2, I get 9 ln of z. All right, let's use our power rule. This is going to give me the ln of 4 cubed is going to be 64. So 64x cubed, and then I'm taking the square root of that. 4 cubed, I think it's 60, right? 4 to the third. Yeah, 64. Minus still the ln of 3y, and then plus the ln of z to the power of 9. Couple of ways that we could do this, but the first thing that I would like to notice, everything that is positive will be a factor of the numerator, everything that is negative will be a factor of the denominator, and so how I would just kind of jump in and solve this is just ln of the square root of 60, well, let's change our ordering here, ln of z to the 9th times the square root of 64x cubed, all divided by 3y. And that is certainly sufficient. Right, so positive ends up in numerator, negative ends up in denominator, and positive ends up in numerator. And when I say ends up, I mean is a factor of. All right. 11's not too bad. You could either match the bases or you could do exactly what we do here for 12. Looking at 12, though, this is 2 to the x is equal to 7 to the 2 minus x. Couple of different strategies to use here. I think the one that I'm going to default to, if you've been changing the bases and that's been nice and you want to continue doing that, go for it. That's perfectly sufficient. That will work really, really well. No problems with that at all. But if that has been confusing, we're going to do this newer way that I showed, which is taking this statement b to the y equals x and rewriting it as a logarithm, log base b of x equals y. Right. In this case, I am then able to rewrite what we see here as log base 2 of 7 to the 2 minus x is equal to x. Double check that, make sure that makes sense. The other way that you could do this is log base 7 of 2 to the x equals 2 minus x. Either way is perfectly fine. Either way is perfectly sufficient. I'm going to stick with what we see here, though. Power rule lets me drop down my 2 minus x. And from here, we are just solving a fairly nasty, but overall just an algebraic expression here. So I've got x on both sides of my equation. I need to get all of my x's to one side, all of my not x's to the other. I'm going to distribute this constant through. We've seen this many times. This is going to be 2 log base 2 of 7 minus x log base 2 of 7 is equal to x. And then moving all my x's over to one side, 2 log base 2 of 7 equals x plus x log base 2 of 7. Normally, we would then combine like terms. Obviously, in this case, we can't really simplify log base 2 of 7. And so we are going to instead factor out an x. Whoop. Don't forget the x times 1 plus now log base 2 of 7. And then dividing by this coefficient here, I get that x is equal to 2 log base 2 of 7 over 1 plus log base 2 of 7. Not the only answer that you could have gotten here, but all of the other ones should be equivalent. You can plug them into a calculator to confirm this. All right. For 13, actually, you know what? We are going to go ahead and solve 11 here. I do want to show this. So this is 4 to the x plus 3 is equal to 8 to the x minus 2. Now, we could do exactly what we saw here. It will work. It will certainly work. But there's a much easier way. The reason why we had to resort to this is because there's not an easy way to write 7 as a power of 2 or 2 as a power of 7. That's really not all that easy to do. Here, though, there is a nice unified base that we could write both of these as. For instance, I could rewrite my right-hand side or my left-hand side here as 2 squared to the x plus 3, and I can rewrite my right-hand side here as 2 cubed to the x minus 2, and simplifying this, I get 2 to the 2x plus 6 is equal to 2 to the 3x minus 6. B to a power equal to b to a power tells me that my powers must be equal. We can drop the bases, set these powers equal to each other. 2x plus 6 should equal 3x minus 6. And I get that x should equal 12. All right. Let's take a look here at 13. So this is the ln of negative 2x squared minus 7x equals the ln of x minus 2. Now, just like with our former problem, in this case, the whole deal of b to the x equals b to the y implies that x equals y. Just like that, we also can say that if I have log base b of x equals log base b of y, then also x must equal y. These are our one-to-one properties. All right. And so let's take a stab at what we see here. I already have this kind of setup where I have my access to my one-to-one properties. So I'm going to go ahead and rewrite this as this must be negative 2x squared minus 7x equals x minus 2. We are now solving a quadratic. I'm going to move all my stuff to one side, offset from 0. I'm going to try and make it so that my leading coefficient is positive. So adding 2x squared, adding 7x, I get that 2x squared plus 8x minus 2 is equal to 0. I'm going to divide everything through by a 2 as well. X squared plus 4x minus 1 is equal to 0. All right, we are now solving a quadratic. We are going to use, in this case, the quadratic formula. Not really any other choice. There are no two numbers that multiply to make -1 that add to make 4. And so we use our negative b plus or minus the square root of b squared minus 4ac, all divided by 2a, all divided by 2a. -4 plus or minus the square root of 4 squared minus 4 times 1 times -1. Now, you absolutely could have used the unsimplified version here. That would also work. You should get the same answer regardless of what you use. And so I get -4 plus or minus the square root of 20, all divided by 2. Go ahead, plug that into your calculator. So -4 plus -4 plus square root of 20 divided by 2. I get that this is either 0.24 or that this is -4.24. Makes a lot of sense. All right, am I done? Unfortunately not. Unfortunately, we also need to check to see, are what we have here actually solutions or are they extraneous? So taking these and plugging them into my function, easiest one to plug them into is going to be x minus 2. And unfortunately, the ln of 0.24 minus 2 is equal to the ln of negative 1.76. Which does not work. And so this cannot be a solution. Likewise, the ln of -4.24 minus 2 equal to the ln of -6.24 also does not work. And so this has no solution. All right. Taking a look at 14 and 15. For 14, we're given that this substance, cesium-137, decays at a rate of 2.31% per year, trying to find the half-life that corresponds to. A couple of different ways that we could do this. Half-life is the amount of time where we have half of our remaining stuff. So in particular, 1/2 of our initial should be equal to a sub 0 times e to the negative 0.0231 times t. And from here, we could solve for t. Notice dividing by a sub 0, I get that 1/2 is equal to e to the negative 0.0231 times t, and then rewriting this as a logarithm, that the ln of 1/2 equal to negative 0.0231 times t. T I get is ln of 1/2 divided by negative 0.0231, which works itself to be about 30 years. All right. Alternatively, we could have taken this r and set it equal to the ln of 1/2 divided by whatever our half-life is, and then solved and gotten the exact same thing. So that this half-life would be equal to the ln of 1/2 divided by negative 0.0231. Certainly also totally fine. Notice that we get the exact same thing that we got up here. Either way, perfectly acceptable. Looking at 15, we are told that we have a starting amount of 400 milligrams, trying to figure out how long it will take until we only have one. So in this case, we are told that A of t is equal to starting amount of 400 E, and we could use like the ln of 1/2 over 30, but why do that when we're already given the r? This is negative 0.0231 times t, and we want to solve for when 1 is equal to 400 e to the negative 0.0231 times t. I get that 1 over 400 is equal to e to the negative 0.0231 times t, and that the ln of 1 over 400, rewriting this as a log, is equal to negative 0.0231 times t. Dividing both sides, I'm going to go ahead and plug this into my calculator. Ln of 1 over 400 divided by negative 0.0231. I get that this will happen in 259.4 years. All right. Let's take a look here at 16 through 18. All of these dealing with the same kind of setup. In this case, this is going to be Newton's law of cooling. So just a reminder, T of T equal to A e to the RT plus T sub S, where A is that initial difference in temperature. We are told that a 5,000 degree knife is placed into a freezer set at 5 degrees Fahrenheit, and that after 3 hours, the knife has cooled down to 500 degrees. So let us take a stab at this. Our environment is going to be that freezer temperature there, so T sub S equal to 5 degrees Fahrenheit, our ambient temperature, if you will. Our initial object's temperature, 5,000 degrees. Very cool. And so that initial difference in temperature there is going to be 4,995. I get that T of T should be equal to 4995 e to the RT plus 5. So what's the only thing that we are missing from our equation? Well, the only thing we're missing here is this value of r. How do we find the value of r? Well, in this case, we're told that when T is equal to 3, my temperature will be 500. So 500 equal to 4995 e to the 3r plus 5, where now our T is going to be in hours. Subtracting 5, I get 495 equal to 4995 e to the 3r. Dividing both sides, 495 over 4995 is equal to e to the 3r. And rewriting this as a logarithm, that 3r is equal to the ln of 495 over 4995. Dividing both sides by 3, I get that r is equal to the ln of 495 over 4995, all divided by 3. And so my final equation, T of t, equal to 4995 e to this r, ln of 495 over 4995, all over 3 times T plus that ambient temperature, in this case 5 degrees. All right, we are then asked to use that to figure out how long it will take the knife to cool to 70 degrees. So in this case, 70 should be equal to 4995 e to the ln of 495 over 4995 over 3 times t plus 5. Solving here, I get that 65 over 4995 is equal to e to the ln of 495 over 4995 over 3 times t. And then rewriting as a logarithm that the ln of 65 over 4995 is equal to the ln of 495 over 4995 over 3 times t. Solving for t, multiplying by the reciprocal, I get 3 ln of 65 over 4995 over the ln of 495 over 4995, which is not very useful. So let's go ahead and actually see what that's going to be. So 3 ln of 65 over 495 divided by the ln of 495 over 4995. I get that this will take about 5.6 hours. Okay. And then lastly, what will the temperature of the knife be after 24 hours? We're looking for T of 24, which is going to be 4995 e to the ln of 495 over 4995 over 3 times 24 plus 5, for which I get e to the I get that this is going to be effectively 5 degrees. This is like 5.0000005 degrees Fahrenheit. So basically 5 degrees. All right. We're going to take a look at 20 here. For 19, arithmetic versus non-geometric, just is it an addition pattern or is it a multiplication pattern? So for instance, notice that for, let's look at just like the first one here, 1, 4, 7, 10. What is my pattern that is moving me from one to the next? This is going to be +3 each time. And so this would be arithmetic versus, say, tricky one. We'll look at -3, 3, -3, 3. what am I doing to move from one term to the next here? In this case, actually, I am multiplying by -1 each time. Since I am multiplying by the same thing, this would be geometric. All right. I will leave the rest as an exercise to the reader. Looking at 20, we are trying to find the 20th term of the sequence. This is 1, 3/2, 9/4, 27/8, so on. Okay, so what do I notice about this particular example? Well, first of all, is what I'm looking at going to be an arithmetic sequence or a geometric sequence? I'd like to make the observation that we are multiplying the numerator by 3 and multiplying the denominator by 2. In particular, that tells us that our R value is in fact going to be 3/2, multiplying the numerator by 3, the denominator by 2, where we know that a sub 1 will be equal to just 1. Okay, so this is definitely geometric. We're multiplying the numerator, multiplying the denominator. And so what is our a sub n going to look like? In this case, a sub n is a sub 1 times r to the n minus 1, taking where we start, multiplying by r n minus 1 times. This is going to be 1 times 3/2 to the n minus 1. And a sub 20 is going to equal 1 times 3/2 to the 19. And we could plug that into our calculator and get some nasty decimal, but I am perfectly happy with just circling that answer and calling it a day. All right, one final one. Looking at 21 here, we're asked to find the sum of the first 20 terms of our sequence here. 1, -1/2, 1/4, -1/8, so on. So again, what kind of sequence do we have here? Well, we are multiplying by -1/2, and so this is going to be geometric, where our a sub 1, just like before, equal to 1. So if we're looking at the sum for a geometric, this is a sub 1 times 1 minus r to the n, all divided by 1 minus r. And so I get that this is 1 times 1 minus -1/2 to the n, all divided by 1 minus -1/2. Which will be equal to, for s sub 20, 1 times 1 minus -1/2 to the 20, all divided by 1 minus -1/2. And again, why are we going to do more work when we can instead just box our answer and leave it there and call it a day? All right. So hopefully this was helpful. Just taking a look at how we walk through each of these various types of problems. And so to that end, if you have any questions, of course, feel free to reach out. I'd be more than happy to help. But I wish you all the best of luck with your studying, and that you all take care and have a good rest of your afternoons.